Hey everyone, welcome to another episode of Conversation with an Astrophysicist. It's been a little while. I'm your host, Scott Lewis of Know the Cosmos, and with me as always is Dr. Katie Mack from Melbourne, Australia. How are you doing, Katie?
I'm all right. How are you doing?
I'm good. I'm not as jet lagged as you are. You've been traveling all over the world and then traveling again tomorrow, so I'm glad we're able to see
Yeah.
you then. And
Yeah, I
I'm kind of
was
jealous, kind of really jealous.
yeah, I had a good trip. I had a good trip to Peru and the Amazon, and it was great. And I got back on Tuesday, and it is
Mhm.
now Saturday, and tomorrow, Sunday, I'm flying to Aspen, Colorado. And I'll be there for 2 weeks. So I'm not yet over jet lag from Peru, but that's okay because I'll be in LA and then in Aspen, and I'll just start over.
Yeah, like you don't need a clock. You just whenever it's sundown, you'll just try to sleep.
I'll get up when the alarm tells me to get up, and I'll go to bed when I can't stand anymore, and that'll be fine.
Yeah, that's healthy. It's a healthy way of doing things.
Yep.
So, well, it has been a while, but
Yeah.
what we'll do real quick is before we get started, let's go ahead and let everyone know how you can talk with us. The best way for us to be able to see your questions and comments is using the Q&A app here, either on Google Plus or on YouTube. So if you look down there, there'll be like a little yellow box that says that we're answering your questions. I see that Paul Stewart from New Zealand has already told us afternoon. It is afternoon for you guys. It is the evening
Yes, it
here
is.
in LA, but you're in the future, so
Yes.
so you can do that. Also, we have our Twitter handles down here too. So I'm at Scientific Scott on Twitter, and Katie is at Astro Katie. So we'll be trying to keep an eye on there. And then you can also comment on either the event page or on the YouTube comment system. And I have that pulled up so we can take a look at there. So we've talked about a lot over, gosh, how long have we been doing this? For a while.
I
But
don't know.
we've
Wow.
gone over
Yeah.
supernovae and dark matter and the
Mhm.
cosmic microwave background. And so
And
let's hit
pulsar.
something that's a big hitter as far as the majority of the universe, dark energy.
Yeah.
But the biggest thing about it is it's the thing that we know the least about. Is that right?
Yeah, I would say so. I mean, in terms of like ratio of how much of the universe it is versus how much we know about it, dark energy wins by a huge amount. Like,
Would you say like
because it is,
68.3%? Is that
yeah,
how much it went?
it's like it's almost 70% of the universe in terms of like adding up its, energy density. Um, and we know a very small number of things about dark energy. Um, so yeah, so I have this. So I have a pie chart of how much of the universe dark matter, dark energy, and regular matter are, which you're bringing up now.
Yep.
Yeah. Okay. So this is a pie chart of the universe. So this is like what the universe is made of in terms of like the stuff that's out there and how much sort of energy density it has. And that big green section is dark energy. That's at last count about 68.3% of what the universe is made of. Then there's the next section, the blue section, 26.8% of the universe is dark matter. That's the thing I study, and we know a lot about dark matter. You can check out our previous videos about dark matter to find out more about that. And then that little tiny slice that says atoms, 4.9%, that's all the stuff that we know, that we really understand. So that's all the things that are included in our standard model of particle physics. So we've got, atoms, neutrinos, even also, even radiation is actually included sort of in that slice. That slice should be sort of just stuff we understand. If you
Yeah.
actually
We
make the
understand less
radiation,
than 5% of the universe.
yeah,
Fully
yeah,
understand, right?
yeah, yeah. I mean, if you make the radiation slice, put that on that chart, it's really small, so you don't really see it. But yeah, so that there's that little fraction that we understand. And dark energy, we know a couple things about it. I'll talk about that in a moment. But it's basically I think, one of the biggest mysteries in cosmology today. Now, back to that pie chart, I just want to, for sort of future reference in this conversation, mention a parameter called omega. So when we talk about how much of the universe something is, we use the parameter called omega, and there's like omega matter is how much of the universe is matter. So looking at this chart, we can see that somewhere around 30% of the universe is matter. So omega matter would be around 0.3. And then there's omega dark energy, and omega dark energy would be, 0.683. So it's the fraction of the universe that is made of that stuff. And I'll come back to that in a bit. But if I talk about omegas, or if you see them on a plot, that's what that's talking about.
Got it.
Okay.
I was
So,
wondering there, we're talking about fatty acids, what type of omegas we're going into, but that makes sense. We're talking about just the percentage of the universe or something.
Yeah, and we use the Greek letter omega, the capital omega, to represent like the fraction of the whole universe that thing is. Okay, so the idea of dark energy, in a sense, goes back to Einstein, and I'll get into that a bit later. But our sort of current understanding of dark energy comes from trying to figure out how the universe is going to end. So in the 1990s, there were a bunch of observations going on to try to determine basically if we're going to have a big crunch.
Right.
So we
because
know
at that time, we just knew that the universe was expanding. We didn't know how it was expanding yet. Yeah,
so we knew the universe was expanding, and our basic understanding of that was that there's something happens in the Big Bang. Big Bang starts off the expansion of the universe, and gravity kind of slows that expansion down. So it's like, something's kind of expanding, and then the gravity is trying to pull it back together. And so there were a few possibilities for what could happen. The first one is, the Big Bang happened in the past. The universe had been expanding. It's always been slowing down because gravity has been pulling it back together. And at some point in the distant future, it's going to come back and crunch, and you'll have a big crunch in the future. And then there's another possibility is that there's sort of just the right balance between the amount of expansion energy put in at the beginning and the amount of gravity trying to pull everything back. And so it's sort of this like constantly decelerating but never going to actually crunch kind of universe. And then there's a possibility that the expansion energy was so strong that the gravity is kind of not that important, and it's just this sort of constant expansion. And those are sort of the possibilities that we thought of. And it's sort of, you could make an analogy with throwing something in a gravitational field. So if I throw this ball straight up, I give it some initial energy.
Is that the Earth? From the Earth?
Yeah.
Oh, nice.
Yeah. Sorry, Planet.
I was wondering what was going on over here. I know we're on the other side of the planet.
Yeah. So if I'm throwing this up in the air, I'm imparting some initial energy. That's like the Big Bang, and then gravity is pulling it back, and so that's why it's always slowing down when it's on its way up, and then so it slows down for a while, stops, and then falls back down to my hand, right?
Right. So it's constantly accelerating towards the Earth, right?
Yeah. So the upward motion is decelerating as it's going up, right? And so there are a couple of possibilities that what could happen with this ball. I throw it up in the air, it slows down, stops, comes down. If I were extremely strong, or on the moon or a comet or something, conceivably I could throw it fast enough that it would escape the gravity, and it would reach escape velocity and be gone, and it would escape the gravitational pull, and that's sort of like this universe where you have just the right balance, where it'll always be slowing down, it'll always be pulled toward the Earth a little bit, but it will not fall back down. And that was the sort of second possibility, where you're always slowing down, but you're never actually going to collapse.
Right.
So those were sort of the possibilities that we were thinking about back in the 1990s. I say we as like the astronomy community.
No, it was just you and me. You and me back in the 90s. We're just hanging out thinking, you know what? This is what's going to go on.
I was in high school. But, whatever. So those were the sort of possibilities that were being considered. And so they set out to measure the deceleration parameter. And the deceleration parameter would tell you exactly how much the expansion is slowing down, which is like, if I throw this ball and you're seeing it on the upward part, you can kind of tell by how much it's decelerating and how fast it's going, you know, how soon it's going to fall back, or if it's ever going to fall back, right?
Right.
You can measure it that way. And so, so this was the plan. And so the way to do this is to look at supernovae. So there are certain kinds of supernovae that have this cool property where it's called a type 1a supernova, and we talked about supernovae in a previous video, so you can check that out if you're interested in the details. But a type 1a supernova is it's a thermonuclear explosion of a white dwarf star, and there's certain like properties of this that are sort of universal. So all white dwarf stars explode in kind of similar ways. And so you can tell by the brightness of the supernova or you can tell by by how the supernova gets bright, how long that takes, and the sort of light curve of the brightening of the supernova, what the total energy of the supernova was, and then you can see it really far away, so you know how bright it was. And so that gives you a way of it gives you like a checkpoint in the universe at different distances along the expansion. So you can look at, yeah.
So, we call it a standard candle, but in this way, it's a way that we have a pretty definite, or as definite as possible, way of measuring distance. And then by knowing distance and brightness, we can see how far away it is, or if it's moving towards us or away from us.
Yeah, so we can use the redshifting, which is the Doppler shift to light, to see if it's moving, how quickly it's moving away from us, and then we can use this this property of the light curve to figure out its actual luminosity, when we also know how bright it is, because we can see how many photons we're getting from it. So I have a little animation of that.
Yeah, let's take a look at it, because it really helps taking. So let's.
Yeah.
And I've just got this on repeat so we can look at it.
Okay, great. Yeah, so this is actual, on the left-hand side, there's a picture of a galaxy and a little bright thing that happens in the galaxy. And I think these are actual images of that supernova as it's getting brighter and dimmer. So that's an exploding star in that galaxy. And on the right-hand side of the right panel of this image, of this animation, you have the light curve, which is sort of measuring just how bright the thing is. And so you can see that at first it gets really bright fast, and then it sort of fades away slowly. And underneath that light curve is the spectrum of the supernova, and just showing how it gets bright in different colors, and the colors are sort of changing over time. So you can use all that information to tell how far away, pretty exactly, that galaxy is where the supernova is going off. And if you look at galaxies at different distances, you're looking at different times. Because as you look at a distant thing in the universe, you're looking at farther into the past. And so that allowed us to sort of measure out the expansion history as a function of time, and use that to kind of figure out what the mix of, how quickly the universe is expanding, and what, the point was to find out how quickly the expansion is slowing down. Okay, so so we have a plot of sort of where that data lies, that shows different possibilities for the mix of stuff in the universe. And so this plot has, so you can see there's a today line, and then there's time going negative, which is like the early times, and then time going positive, which is what's going to happen in the future. And there are a few different lines there. So the red line that curves up and down, that's a big crunch cosmology.
I'll do the sound effect for this.
Okay, great. And so that's a universe with omega matter equals 8, which means that you have way more matter than you need to close the universe, to make it something that will collapse in a big crunch. And then there's the green line, which is a omega matter equals 1 universe, which means that you have 100% of the universe that's needed to sort of keep the universe like full, basically, is matter. So the universe is totally matter dominated, and so that's what the sort of past history of the universe would look like in future history. So you see, it's never going to crunch. It just kind of it is sort of always slowing down a little bit, but it never actually comes to a crunch.
Right.
And then the supernova data are these black and red dots on the plot. Mm-hmm. I'm like pointing to the screen. I don't know why I'm doing
that. That helps. I'll use my mouse.
That's a better idea. Sorry. Anyway, so what we saw was that the supernova data lay along a totally different line, and that line was a line with omega matter equals 0.3. So the matter was 30% of the amount of matter needed to keep the universe like exactly balanced at this, sort of where it would just coast forever. And then there was this other term, dark energy, which was 0.7. So like 70% of the universe roughly is something else, in this case called dark energy, where you can see that in the, I'm not going to point at the screen.
Point at the screen, yeah, no.
No, so the future of this cosmology, the scale factor, which is like the size of the universe, is increasing. And so at the present time, at the today mark, the deceleration is not happening, it's acceleration. So I have another picture that shows sort of what that looks like in terms of expansion history. Yeah. So what we found was that we live in this accelerating universe where the universe was slowing down in its expansion for a while and now is speeding up in its expansion. It's going to be
a huge surprise.
Expanding.
We weren't expecting this.
Yeah, it was a really big surprise. It was a really, and it's really weird as well. Like, it's a very strange kind of physics. So it's like, I take my ball and I throw it up in the air, and instead of slowing down and stopping and coming back, it's slowing down for a while, and then at some point it turns around and just shoots off into space for no apparent reason.
Right.
Like,
just does. Right.
Yeah, it just does. Right.
Why? Because we don't know.
Yeah. I mean, and in the same way, we don't know of anything on Earth that could make, something suddenly not only ignore gravity, but sort of defy it, potentially. We also don't know what could do that in the universe. Like, there's nothing that's part of our sort of standard understanding of cosmology that makes the universe suddenly start expanding faster. And so there is a small exception to that, which is that there is a concept that dates back to Einstein that does have this kind of behavior, but we really thought it wasn't real. So this is...
It came out to where he thought it wasn't real at the end.
Yeah,
and then it ended up being kind of real. Right.
Yeah, so this is of course the cosmological constant, which apocryphally is called Einstein's greatest blunder or something like that. What happened? The cosmological constant is a term in the equations of gravity that is sort of an anti-gravity term. It's something that counteracts collapse. So you have the whole universe is trying to collapse because there has gravity in it, and the cosmological constant is something that kind of pushes back, right? That pulls the universe out again. And the reason that Einstein introduced this into his equations is because he didn't know that the universe was expanding, but he knew that it hadn't collapsed on itself. And so he knew that gravity would want to make everything collapse on itself, and he needed something to hold that back. So he thought the universe was static. He thought the universe was in a steady state where it was not expanding or contracting. And it certainly was reasonable to assume it wasn't contracting, because why would we still be here if it was contracting? It probably should have contracted a long time ago. Right. And so he thought that, you needed something to counteract that gravity. And so he threw in this cosmological constant. Shortly afterward,
just to balance his equations, right?
Yeah, yeah. I mean, and it made sense. But shortly afterward, he found out the universe was expanding, and so he realized that expansion, that initial expansion push, could be enough to keep the universe from having already collapsed. It could still be expanding, and gravity could have not yet sort of caught up or not be strong enough to catch up and pull everything back. And so he threw that term away. But after we found the universe was accelerating, we needed something to push back against that expansion.
We needed to put it back in, right?
That collapse, so we put the cosmological constant back in, And so we usually use the Greek letter lambda to represent that. And so I have another plot, which is this triangle diagram that kind of shows
triangle actually.
Yeah, so this is a confusing but kind of cool plot of different possible cosmologies in the universe. And so this is a plot where you have three axes. You have the matter, the K is like the curvature, and then you have lambda, which is the cosmological constant. And so so the curvature pertains to the universe could be flat or it could be curved, and a curved universe is one where like straight lines do not stay parallel. So if the structure of space-time is curved, much like that near a gravitating object, space-time is curved. So parallel lines trying to move past a gravitational object will converge. So you can have curvature near a gravitational field, but the larger universe, like as a whole, you could also have curvature. So if the universe is overclosed, for instance, if there was too much matter in the universe, that would be a closed, curved universe that's curved sort of inward, right? So it turns out, it seems that the universe is flat in the sense that we have just enough matter and dark energy to kind of balance everything out, and straight lines stay parallel. So that's that line there where omega curvature is 0, omega k is 0. So there's no curvature energy or whatever, no curvature component of the universe. And so if you look at different points on this plot, you can see different possible universes. So the SCDM is where you have 0 dark energy and you have 100% matter. So omega matter is 1, omega lambda is 0, and omega curvature is 0. And so that's sort of like standard cold dark matter. So it's dark matter dominated and it has regular matter in it, and it's not gonna collapse. It's just sort of a steady one, perfectly balanced flat universe. And then the top one is open CDM, so that's a universe with dark matter in it that's open. So it doesn't have enough matter in it to close it. So it'll expand forever. And it has curvature, as omega k is, I guess in this case, 0.75 or something like that. And that's an open universe. And then you have the universe that we seem to live in, which is the lambda CDM universe. And we talk a lot about the lambda CDM model. That's sort of the concordance model of cosmology, where we have a flat universe that has no curvature, but it has about 0.75 of lambda, dark energy, 0.7, whatever, around there. And then for omega matter is this small percent of about 30% matter. So that's sort of where we think we're living. And it's weird, right? Like
it is weird.
So we seem to be in a universe that is dominated by this dark energy. We call it dark energy because we don't know what it is. It seems to match all the properties of a cosmological constant. There are certain properties of the cosmological constant. One of them is that the density of the cosmological constant is constant. And this
is that what they call it, the cosmological constant?
Yeah. And this is weirder than it sounds. Okay, so for instance, the density of matter in the universe is not constant.
Right.
And the reason for that is that the universe is expanding. And as the universe expands, the matter in it gets farther apart. And so the density, if you take like a box of the same size at different times, the density in that box is less because the universe is getting bigger.
Right, because density is just the amount of stuff within a volume, and if your volume keeps getting bigger, obviously your density is going to go down as long as no more stuff is being added to it. Right.
And so over time, the density of matter goes down. That doesn't happen with dark energy, with the cosmological constant, rather. With the cosmological constant, let's say you have a box this big, and you have a certain amount of cosmological constant in it, and you suddenly make that box twice as big without opening it, now you have twice as much cosmological constant because the density has changed and the density has not changed. So the density is the same. So if you make the volume bigger, you have more cosmological constant. And that's also really weird. I mean, so we've got the weirdness of, counteracting gravity, and we've got the weirdness of the density not changing. And so because that density hasn't been changing, as the universe has been expanding, dark energy, or the cosmological constant, has become more important over time. So we are now in a lambda-dominated universe. We're in a dark energy-dominated universe. In the past, we were in a matter-dominated universe. So there were, at earlier times, the universe was smaller, the matter was closer together, the density of matter was more important than the density of dark energy. Now, as the universe has gotten bigger, the density of dark energy is more important, and that'll always be the case if it's a cosmological constant, because everything else, the density is decreasing as the universe is getting bigger. That's not happening with dark energy, with the cosmological constant.
And
so,
do we have any idea why that's the case? I mean, I know that we're having a difficult time, directly detecting dark matter, which is nothing related to this at all, except for trying to, hoping that it would squeeze back down on itself, and it won't. So with dark energy, how could you directly detect that besides just watching the universe infinitely expand?
I mean, basically, so there are a couple of like laboratory experiments testing weird sort of small scale physics phenomena that might be related to dark energy, if dark energy is something like a vacuum energy of the universe, which is sort of what a cosmological constant kind of is, although the scales are off in a weird way.
I have a feeling we're going to have to come back to that on another episode.
We might have to come back to that, yeah. But in terms of like actually measuring the dark energy out there, I mean, it seems to be uniformly distributed throughout the universe. It doesn't seem to change with time in terms of its density. We can measure the expansion history of the universe very, very carefully and see if we see any deviation from a cosmological constant, which so far we have not. We can measure how structure forms over time and look for variations in that might be different with different models of dark energy. So far, everything looks like a cosmological constant. There's not like a stuff to detect exactly.
Right.
If it's a cosmological constant, it's kind of just part of how the universe is, and that's sort of frustrating.
Well, yeah, because it's so weird from what we see every day. I mean, everything we experience here on Earth, or even just with our observations locally, we don't see anything like that. Everything pretty much stays generally to Newtonian gravity. We can plot orbits and things like that. Yet everything else really in the universe, when you look at it in this large scale, is doing completely the opposite of what we see in our neighborhood. Yeah, I mean, on the largest scales, things are just not acting like our sort of our experience suggests they should. But yeah, so it's mostly measuring the expansion, measuring the growth history, in order to try and figure out what dark energy is. And then there are a couple of other things, looking for modifications of gravity that could be due to something that also relates to dark energy. So there are lots of tests of gravity on various scales to see if some modification of gravity could be responsible for the observations that we're seeing. At the moment, it really looks like the expansion of the universe is accelerating. And that's a bit like, that should give you a pause a little bit, because it means that over time, the universe is going to get more and more stretched out and more empty, and it'll eventually lead to what's called the heat death of the universe, where you have so much space between things that you can't bring anything together to make new stars and stuff, and you run out of sort of fuel. You run out of energy differences between things, and you can't do life or chemistry or any computations or work. Yeah, and so eventually the universe ends up cold and dead and boring, empty, basically. So that's fun. Like my heart.
Yeah. So
Real quick, because we have run out of time, but I'm just gonna answer a quick question here from the Q&A app here from Mark Carlin. Said, if space expands, how can gravity make the universe collapse? And that's the whole point, is that it's not. As far as we see, it's not doing it.
Well, I mean, yeah, gravity is it does sort of try and collapse the universe. It does pull things together. And compresses space-time, but the space is has been expanding, and if it weren't for dark energy, then the gravity of everything in the universe would slowly be counteracting that initial sort of energetic push of the expansion from the Big Bang. Because of dark energy, it does, that expansion seems to be winning, and it seems like it's going to keep winning. I wanted to show a little image I put together as a disambiguation between dark matter and dark energy, because they're very different concepts.
Let me pull this up.
Okay. So I use this to explain that dark matter and dark energy are probably not related in the sense that they really act very differently. And there are theories that do have connections between dark matter and dark energy, but in terms of how they act very differently. So this is, it's one of these standard visualizations of the fabric of space-time. And as you've seen in many visualizations, you can think of mass as sort of making a little dent in space-time and sort of pulling space-time together. And dark matter is a kind of matter, so it does that. Dark energy sort of pulls space-time apart. It sort of smooths out space-time. So dark energy is the thing that's causing space-time to expand more, and it kind of acts sort of to smooth it out on large scales instead of to bring it together. So yeah, I mean, there are certainly models that do have, connections within the dark sector, where, dark matter and dark energy change into each other in certain situations. But at the moment, I mean, in terms of just looking at how these things act, there's no indication that they're aspects of the same thing or related to each other. So, we don't have a lot to go on in terms of dark energy. It looks like it's probably a cosmological constant. I mean, the expansion of the universe is a huge thing, and that led to a Nobel Prize in 2011 for the expansion of the universe. So that went to Adam Rees and Saul Perlmutter and Brian Schmidt for discovering that expansion. And so, that's considered to be a Nobel Prize for dark energy. It's really a Nobel Prize for the accelerated expansion of the universe, because we still don't know what dark energy is. It looks like a cosmological constant. We may never be able to tell if it's really a cosmological constant or something that just looks a lot like it, because
I think it's kind of cool though, with the fact that you've hung out with, at least I know for sure, Brian Schmidt, because he's given you a plaque for your office, which is awesome. Because Katie is the most followed astronomer in Australia on Twitter. Yeah. Brian Schmidt gave her a gift. And then I've worked with Adam Rees over with Hubble, with the Hubble Space Telescope at Space Telescope. Yeah. So we're like 1 degree away from that Nobel Prize. It's kind of cool.
I've chatted with Saul Perlmutter too. He is really cool to talk to. He's really inspirational about he gets you really excited about supernovae.
I mean, come on, they're pretty exciting, literally and figuratively. I mean, they're really exciting. And with that bad joke, I want to thank everyone for sharing everything out on Twitter and Facebook and Google Plus and YouTube. And we will most definitely have a follow-up episode, but it's not going to be for a while since you're going to be traveling.
I'm going to be traveling. I'm going to be all over the place for a while, but at some point
when we hang out and when you're stateside, we'll see if we're gonna, I don't know if I want to talk work when you're actually in LA. I think we just should hang out.
I'm only there for a couple hours, so
Exactly. So let's just get dinner and hang out. But we will definitely follow up with more on dark energy and the cosmological constant. Please leave any questions that you have for us below, and we'll try to follow up with them. Also, I'm seeing a few things over on Twitter, but not quite related to this, but it's something that we can totally follow up with as well, with more on dark matter. If you want to know more about dark matter, we have, 4 episodes? So watch it. I've playlisted up on this channel. You can watch us there. And it's up knowthecosmos.com. But Katie, again, thank you for carving some time out of your extremely busy schedule.
No problem.
Have an awesome flight out to Aspen, and I will see you when you're heading back to LA to fly. Are you going home, or are you going directly to London?
No, I'm gonna. So I'm going from here to Aspen, then Aspen back to here, and en route back, I will be in LA for like 10 hours or something. And then I'm going to be back here, and then I'm going to Perth, and then I get back here from Perth, and then the next day I go to London.
As one does. The glamorous lifestyle of an astrophysicist.
Yeah.
All right. Well, again, thank you for shocking us with your knowledge on dark energy. And we will see you all next time.
Yep. Bye.
Bye.